Okay, so we're there. So I'd like to introduce first our speaker from KCB, Luke Palmen. He's going to talk about Dambreak modelling development. So we've got three speakers, two live and one remote. Let's see how we go. We've got it on record, so the recording will be made available to people. We're going to try to do it without the microphone, otherwise we get interference. And it's interference not so much for us, well, we get it. We also get it on the online audience as well. And just to give you an idea, participants online, 62. And we probably have a similar number here. So this is a record for the Queensland Tailings Group. Without further ado, Luke, so you know how to operate this, just up and down keys, up and down keys.
Oh, okay, to advance. All right, awesome. Good evening. Thank you. And I first mentioned to one of my colleagues that I'd been asked to speak at the next QTG meeting, and it was actually live in person at the Treasury Casino. And I couldn't remember the last time I'd been to a live event. He stopped me short, looked me in the eye, said, "That seems like quite a gamble," which almost as much of a gamble as opening with such a poor joke. But, you know, here we are. It's obvious I'm not a comedian. I am a civil engineer. I've got about 13 years experience across client and consultant roles in infrastructure and resource industries. My principal areas of expertise lie in hydrology and hydraulics and numerical modelling. And I'm good at that because I thoroughly enjoy getting down to the detailed aspects of that type of work. About 8 years ago, I was given my first opportunity to simulate a dam break. And from that point, it's been an area that continues to capture my interest. So over the recent years, there's been a marked increase in the number of dam break projects or dam break related projects. The increase in work is beyond the natural growth of the industry. And it's a direct result of the numerous well-publicised catastrophes that have played out across our screens over the last 5 to 10 years. Now, as a result, it's seen the industry and the general public reject the status quo of the risk management and operation of these structures. This demand for a better quality and a higher standard in relation to these structures isn't unique.
No.
You're right.
No. So yeah, no.
Okay. This change isn't unique. Government and municipal facilities have also seen a reduction in the apparent risk tolerance from the general public in relation to infrastructure immunity and the consummate increase and demanded design life of public infrastructure. So my presentation today intends to cover some of the developments that we've seen over the recent period. I'll also cover some emerging methods and what will likely be commonplace in the near future. So to cover this scope, I'll approach it in a traditional engineering fashion, which is to try and represent an incredibly complex issue by breaking up into smaller, simplified pieces, solve those pieces, and hope it still represents the final product when we put it together at the end. This way, hopefully, I'll avoid any overly technical issues while still providing enough detail to explain the challenges that are involved. I'll be presenting this from my point of view and my experience, and given the expertise in the room, I'm sure I'll raise some points of comment or conjecture. So please, I'm happy to address those or receive comment at the end of the presentation. I'll start with an overview of an inputs to a given study. Here we have our facility with a finite volume of material, of which it has particular material properties. Its initial state can be described as a solid mass of material with geotechnical properties. There may be some additional event contributors to the breach itself, and then once that material is mobilised, it can no longer be described as necessarily as with geotechnical parameters, and its behaviour may be represented as a non-Newtonian fluid. The run-out behaviour of this material can be estimated using numerical models, and the potential impacts quantified. The run-out behaviour of this material can be estimated, the summation of these downstream impacts form the basis of most regulatory and industry-guided consequence category selections. So initially, we'll look at the material and volume aspects of the system. I recall my first application of a TSF dam failure some years ago I used a simple run-out formula that was based on the estimation of shear strength and assumed volume of tailings based on a block or a triangular wedge of tailings material, and that was it. There was no run-out. Well, that was the run-out extent. At the time, that was a fairly simple analysis, but it also wasn't uncommon to see non-Newtonian behaviour being completely ignored by modelling the facility as water. Sometimes this was due to the absence of information, sometimes it was due to limitations in software or expertise. The outputs were generally presented as being conservative, however, there isn't really a whole lot of evidence to support that position. Ultimately, these methods ignore most, if not all, of the flow properties and characteristics of the material that are actually within the TSF. Current practice, in line with recent guidance like CDA, uses an assumption of a mobilised tailings volume based on a geometric method. In this way, we can at least consider the height and the geometry of the facility. We create our post-failure surface, which then holds our nominated volume of mobilised tailings. One of the more influential parameters in those series of assumptions or estimations is that post-failure angle, being the main sort of driver of the overall volume. This method is far better than, say, assuming a third of the total facility or other sort of empirical relationship, but it's still a fairly weak connection to what's actually happening within the TSF and the actual geotechnical state of the materials. Once we have our mobilised volume of non-Newtonian behaving material, we provide the numerical model with some parameters to describe how that fluid behaves for a given solids content. A process that also has its fair share of assumptions and potential areas of error, and it's how it responds to shear. A couple of things to note is, again, there's some assumptions related to the density of the material. We can look at the density of the in situ material. We can look at the relationship between its sorry, I've just lost my place. It's not necessarily the run-out material's solid concentration is not necessarily the same as what it starts when it's in situ in the facility. Once flowing, it can vary in void and moisture content. Secondly, it's in its real state, there's obviously a lot of variation between the tailings material, whereas the most common approach is to adopt the whole facility as one particular homogeneous material. This plot here shows shear stress relationship with shear rate, and you can see from the top of those top two curves, the same TSF samples approximately 50 to 100 metres away from each other, and the solid content of those two top curves are within 1% of one another. However, as you can see, its behaviour in response to shear is markedly different. I'll revisit this later, but from this point, we've got material properties that we can represent within our numerical model. And one of the shortcomings of the state that I've just described, or the description I've just described, is that we don't actually capture the change in state from a solid to a non-Newtonian fluid. We're starting with the non-Newtonian fluid within the facility. However, there is some development in this area. Over recent years, the development of material point method models have allowed us to describe some of the deformation behaviour of these materials within the facility. An MPM model, I'm sure you are more familiar with most of it than me, is somewhat similar to a CFD model in terms of how the model is schematised and there's significant demand in computing power. Various forms of MPM model have been used to benchmark historical failures, including Brumadinho as well as others, where it's found to produce results that can be consistent with the observed behaviour when using the best estimates of geotechnical properties. So, and that's one of the main lures of this type of model, is that depending on the solution scheme, it can utilise geotechnical terms to describe the change in state of the material within the facility, honouring the mass, momentum and water content of each region of that material prior to it becoming a fluid-like flow. So awesome. Why don't we just do the whole system using this model? And that will be great when we can do it. I don't know if we're quite there yet. Some of the restrictions are the solution schemes and whether or not they can represent all of the different states that the tailings will go through from solid to a fluid, as well as the computational demand that it takes, and then applying it in a commercial sense. For example, for one of our recent projects, we created some very simple MPM models. It's just a 2D slice with one material type, with the intention of using the model purely to support the selection of a post-failure angle slope. We considered 3 different locations with either a dry or a saturated material. The computation for approximately a minute of runtime was varied between days and weeks, just running on the back of the office machine, whirring away. However, the actual results were really promising. The estimated post-failure slopes were consistent with the various estimates and ranges that were developed from previous studies and other material characterizations. And so suddenly we seem to have a geotechnical model that's able to describe the high rate of deformation, which we didn't really have before. It also provided the potential to inform other parameters, most of which are parameters that are generally assumed or estimated in other parts of the study, such as the overall failure duration, the total mass movement over time, particle velocity through the breach, and the change in solids content, all of which can be used to dial in or calibrate another 2D model or a simpler 2D model. So while the ultimate goal may be to simulate the whole system, the low-hanging fruit that we can use the models for now is to inform other more simple models with the parameters that we generally assume or pull from empirical studies. So back to our simplified model inputs. We'll skip over the hydrology for the moment and we'll go straight to the breach component. This is another area where traditionally what we've modelled may not have a whole lot of connection to what's actually present within the facility. This issue is likely to be a result of the lack of information relating to how a breach may develop in a TSF. And given that lack of guidance, the fallback option has generally been to make the assumption that the breach may develop in a similar fashion to a water dam. And while that may be true in some instances where you've got a lot of water and a soup like TSF, and the main contributor to a breach might be an erosion-style breach, there's very little understanding of how the tailings material influences that process. And we're not representing pure liquefaction failures where you get whole embankments removed. However, there is some improvements that are available. For one of our recent projects, for a study, this was for a water dam, we used a probabilistic Monte Carlo model to investigate just how much different breach parameters affected breach outflow. So we used industry guidance to put bounds on different parametric breach parameters, such as time to failure, breach widths, depths, different weir and piping coefficients. We ran that model 10,000 times with different combinations of those inputs. The output model showed the huge variation in peak flows that we could expect while we move through the different ranges of parameter inputs. There is no reason why we can't do a similar approach to a non-Newtonian dam failure. So remember back when I mentioned the different solids content and how much the shear rate changed between those two samples? That's the perfect sort of, that is the perfect parameter that would be used in a probabilistic assessment for a non-Newtonian dam case. Similarly, the post-failure slope angle would be another one, which is a perfect candidate. Ultimately, what we'd be working towards is a model breach that can be presented as a most likely. So you're still developing your deterministic solution, but you've also got upper and lower bounds based on the combination and variation of input parameters. Now, seeing as we're talking about uncertainty and variation, we'll quickly touch on the hydrologic inputs. So this is a diagram that describes the confidence of design flood estimates across a range of probability. And as can be expected, the less probable the event, the higher the degree of uncertainty. The next plot is a practical implementation of that. This is a calculated peak flow for a catchment where antecedent conditions, so whether it's wet or dry before the event starts, temporal, so it's the rain variation over time, and spatial, it's variation in space. Patterns and losses were all varied using real measured ranges or expected ranges, and it was run a few thousand times, and the peaks were all plotted here. What I'm trying to show is that if you've got a really good hydrologist or flood engineer and on your project, and they have good data and they do a really good job, then you should end up with the flood estimates that follow that curve. However, as the scatter of the plot indicates, your design value might vary by plus or minus 50% relative to just this example. And if we look at the probability, we're only at about 1 in 100. So you can imagine the gain in those confidence limits associated with a PMP or your more extreme events moving off to the right. And so by definition, the PMP being on the edge of credibility would have massive uncertainty attached to it. And so even with a good solid estimate of extreme rainfall, are we adequately representing this in the rest of our analysis, considering how much of an important part it can make to the study? Back to our system inputs. The run-out model area is somewhere where we have seen considerable improvement in terms of the modelling methods that are available over the last couple of years. I'll keep it fairly agnostic in terms of software selection, as I think the most important part is probably having a suitable modeller to drive the model rather than the best model. And they correctly understand the model or the situation that needs to be modelled. So the way that it's typically been modelled historically is to develop a single model representing the facility as a stage storage curve or a 1D model. That model might have a breach as a weir for an overtopping failure, or an orifice for a piping failure. It'll have dynamic geometry that changes its width or elevation over time, and the outcome being a breach hydrograph or a similar relationship of mass over time. This output hydrograph would then be added to a more detailed numerical model of the downstream area. And that separation between models, or decoupling between the facility and the run-out area, can be a significant source of error due to the assumptions in the boundary condition coming out of the first model, and similarly the assumptions that are attached to the input boundary condition of the second model. It can be made to work, but in the majority of cases, not enough time is spent ensuring that the two conditions are consistent between the two models. The way that we've been schematising the model more recently is to include both the facility and the downstream area within the same two-dimensional model. However, we run the model twice, along with, in terms of the CDA guidance with process 1 and process 2 flows. Once for the non-Newtonian fluid, and then we use those results to inform a second model where we run Newtonian fluids for decants, or you've got storm events getting added. And this arrangement means that we're representing two distinct phases of the material, which is fine for scenarios where mixing isn't a considerable input. So if you're running into a waterway or a lake, or you may need to reassess your need for a full mixing model and that behaviour to be represented. So while we remove the one-dimensional model, it doesn't necessarily preclude a smaller model just for the facility in the breach to be developed. Obviously, being a smaller model, you can run it lots of times. It's normally where a lot of churn happens in the work. But the arrangement of this does force the modeller to assess how well the two models agree with one another. Where I see us moving in the next year or so is, well, sensitivity testing across different projects have shown that we can have great, precise downstream models, but the potential variation associated with parameters that we put back up in the facility have a far greater variation and impact on what's happening downstream than the actual 2D model calculation. So obviously getting those parameters up the front right removes that problem, but we know that that's not always easy to do. What we can do, however, is approach the greatest areas of uncertainty with a probabilistic assessment. So rather than us attempting to assign a deterministic single value to parameters that are inherently variable, we can provide a range or a distribution of material parameters, breach widths, post-value slopes, rheological modelling, numerical parameters. And we can either run an ensemble of 10 or 20 simulations, or we can go the full Monte Carlo and do 1,000 simulations, the output of which is a distribution. We can select either the mean or the most likely result, and you can also present your maximum and minimum extreme ranges. So when we develop the output in this way, we inherently carry through the understanding that what we're presenting as a deterministic output may not be exact, and it does have some measure of uncertainty. And so I think this is critical to communicate to our clients and the people that read reports, in that we don't exactly know what's going to happen with the dam breach failure, and we should recognise the potential engineering hubris if we don't make it abundantly clear that the models are an estimate. And so I think we're in a far better position if we present an envelope of outputs and then select one that's described as our deterministic output, rather than the other way, which is more typical, where you present your one output and you say, oh, there's a couple of sensitivity runs either side of it. In our last section, it's the downstream receptors. That is estimating the population, environmental, societal, economic impacts of a particular event. I'll primarily concentrate on the population aspect, as that generally governs a lot of assessments. In most cases, the method that is used is a static assessment of population, basically overlaying the run-out extents on a map of population locations and summing up those affected, which we term population at risk. In some assessments, if we think we have suitable data, and we generally don't, there'll be a fatality multiplier that's applied, and that's the statistical chance of based on historical events, that a person who is identified as being at risk will lose their life, and that's the population probable loss of life. The method is very coarse. It doesn't allow for human behaviour. It doesn't account for varying physical abilities. It doesn't allow, it's very crude in its application of warning time. You either get it or you don't, and you get out or you don't get out. There's no grey area. Some of the more advanced methods are available and that we can use now is life simulation models. So a life simulation model has been around for a number of years, but it got pretty serious following hurricanes Katrina and Rita in the States, or the evacuation of New Orleans and Houston was hampered by traffic congestion and escape routes. For example, I think that first one was Hurricane Rita. It was 120 deaths in the evacuation, which was more than the hurricane. And that's why that's important for that particular scenario. And later, the Oroville Dam incident provided a great data set to evaluate the effectiveness of mass evacuation of urban areas. A life simulation model is a dynamic network model. What that means is for each population location, it's represented individually as a node or a point. Roads or paths create a vector network, and our breach model or flood model or bushfire or lava flow, anything that moves over space over time can be represented. The model allows the population to mobilise either on a warning time or a proximity to a hazard, utilise road and escape accesses with consideration of whether in a vehicle or on foot, and it will then consider the capacity of the road network. It'll determine whether road networks are trafficable or cut off by the hazard. It'll then turn PAR around and find an alternative route. It won't change. It won't work. It won't go back and try the same route again. It can model the differences in survivability between escape out in the open or being in a structure, whether the structure is timber or steel or masonry. All of these things can be put into the model. What I think the most clever part is, and ding, 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 there's a theme here, it's probabilistic. It can randomise using specified distributions what certain parameters are for each PAR point. So not all PAR will take the same route. Not all PAR will react and respond in the same way at the same time. Not all PAR have the same physical ability and survivability. And so the modelling method, I think, provides the closest proxy we have to account for an individual's behaviour and response during an extreme event. when compared to historical events, a well-developed LifeSim model represents the PAR and PLL far more accurately than the simplified methods that are typically being used in static assessments. So granted, the cost and complexity of setup is reasonably significant, especially first off, and it's not going to be economically viable for every application, but it is getting used in mainstream large water dam failures, and it's only going to become more commonplace and used in more and more run-out assessments and facilities. It's definitely the way forward. In summary, we've explored the pertinent inputs to our dam breach models, and I've spoken about how we've traditionally estimated these inputs, how we're currently working to reduce that uncertainty and recognise the variability in results, and what I think we'll be working on in the near term to further improve our assessments. I hope that providing this overview can remind us that the assumed inputs with a great model are still assumed inputs. And then are we suitably communicating that level of uncertainty through the reports to our clients? We all understand that uncertainty is a part of any engineering study, and one that traditionally, through either complexity or convenience, it hasn't been well managed or communicated. In application to dam breach models, I hope that our work and the outcomes from our work in the near future will help plan and inform our clients to the risks and potential consequences that may lie within these facilities. If anybody has any questions or comments, I'd be glad to take them now. To the end? Okay, awesome. Thank you.
We may be getting some feedback from someone on the online audience. So if you've not muted, could you please mute? Now, the next little challenge is, the easy part really is for me to introduce Dr. Behnam Pirouz. He's with ACC Williams. He's based in Melbourne. He's going to talk about a realistic approach to tailings dam break analysis using site-specific parameters and laboratory test data. Now, the only challenge might be, I'm going to stop sharing first, and the challenge might be, can I allow him to share, or can he share?
You want me to try, David?
Say it again.
You want me to try share my screen?
No, you can't yet. I've got to stop sharing first, and I can't get my mouse to work. Just hold on a sec. Stop sharing. Stopped. Don't know why the hell my mouse won't work. Now, finally, the mouse is working out. Get rid of that. Okay. Can you see a slide bar at the bottom, Benoit?
Yep.
Can you try and click on share screen?
Can you see the screen now?
Yes, we're still here now. Yes, you've now come up. So if you could go ahead with your presentation. Thanks very much.
Okay. Can you hear me all right?
Yes.
Okay.
That's fine.
Go ahead.
Yeah, I'm just trying to minimize this banner from.
Don't worry about it. We couldn't last time either.
Yeah, okay. Thank you, David, and good evening to all. The topic of the presentation tonight is just as David mentioned, is realistic approach to tailing dam break analysis using site-specific parameters and laboratory testing.
Someone online has their voice on. Could they mute, please? Someone online is not on mute. Could you mute, please? It's still on. Beg your pardon? It's muted. Okay. Go ahead. Go ahead, Behnam.
Okay. Yeah, that image on the screen is a toxic chemical and tailing release from dams in Russia. That's just to refreshing our memory about the failure cases that happens around the world every year. I'll just go through a few actually dam break examples around the world, just to remind us ourselves that dam break is a reality of the fact that happens every now and then around the world. Tailings dam break analysis is a numerical modeling process which assists to identify potential impacts, social, economical, environmental, from TSF failure scenarios and release of tailing and water from the TSF. The analysis will help to assess the consequence category of the TSF and provide guidance for TSF design and approach and operation. The overview of this presentation is we start with consequence of tailing dam failure, just a review of that, and then why we do dam break and why we need actually to do dam break analysis, different mechanism of tailings dam failures, and then simulating dam break, including input parameters, mathematical model, available simulation tools, and limitations. Then we go through reviewing what we should expect from the simulation and reliability and interpretation of the result from that simulation. At the end, we review the uncertainties in input parameter and how we should do sensitivity analysis of the result and the method we use with the input parameter. The consequence of a tailing dam failure, as we all have heard many times, you know, the recent dam failure in 25th of January 2019, the latest major one was Brumadinho dam failure in Brazil, which cost actually 270 lives. That's an image of the facility before the failure and after the failure. Another one that we're all familiar with is the dam break of Mariana or Samarco dam failure or Fondao dam failure due to liquefaction of saturated sand, the 5th of November 2015, which caused significant environmental impact and also 19 deaths. The other famous dam break that happened a few years back, in 4th of August 2014, is a foundation failure of Mount Pulley that caused resulted in 8 million cubic meters of tailing released to the environment. With that three famous dam break and iconic dam break, tailing dam break, I just wanted to go back to remind all of us that dam breaks of a smaller size happens maybe every month or every other month around the world, but maybe we do not hear about them. This is a few slides from the presentation a few years ago in 2007 in Convention of Transboundary Effects of Industrial Accident by Philip Peck. It shows a dam break, release of tailings and slimes from a dam break in Sasa mine in Macedonia. Again, the contamination of downstream land from the same actually dam break failure, and then the cleanup work after the failure or release of tailings from the dam. Philip Peck, in his presentation, he ended his presentation with conclusion that tailings management facility can and do fail. This can almost universally be prevented. One key area that helps is the good practice in management and operation. With that in mind, knowing that the consequence of the tailing dam failure can actually cause cost life and also can be huge environmental impact. We go to the question that why did we need to simulate dam breaks? The guideline that we usually use in Australia is the ANCOL guidelines, these two guidelines on tailings dam and the consequence category category assessment for the dams. It requires that the inundation depth and velocity mapping for the tailings dam to be prepared and studied. The consequence category severity of the impact, the population at risk, and possible loss of life to be defined in the design as the design parameter for the TSF, and then an emergency response plan to be prepared for the TSF. More recently, the GISTM standard also requires that credible failure scenario should be defined for the tailings dam, and then site-specific emergency preparedness and response plan should be prepared for the tailings for any TSF storage capacity, storage facility. ANCOL guideline, this is an extraction from the ANCOL guideline in 2019. A dam safety emergency plan in conjunction with appropriate emergency authority planning should be prepared for tailings dam where any person, infrastructure, or environmental values could be at risk should the dam collapse. The dam safety emergency plan should include an appropriate dam break study with the conservative assumptions of liquid tailings flow in the event of dam failure, unless a more sophisticated analysis of water and tailings flow can be justified. And that dam safety plan, emergency plan, need to be updated annually and tested at regular intervals. Dam break simulation is undertaken to save lives and improve operation to reduce the environmental impact of TSF failure. Different mechanisms that we can imagine that will cause a tailing dam to failure can be summarized as either a sunny day failure scenario, which is failure due to a previous rainfall event stored in the dam or accumulation of the processed water causing a seepage and piping failure through the embankment structure. Usually the assumption for this sunny day failure is water pond as the maximum operating pond, an opening in the embankment, seepage increases in the embankment, and then gradually it causes to failure of the embankment to a certain height or the total failure of the embankment. Or in sunny day failure can cause by sudden failure induced by earthquake or static liquefaction. The dams store tailings and water at maximum operating point level, all of a sudden due to static liquefaction or earthquake fails. The other mechanism for failure is post-flood failure or flood failure scenario, which usually associated with breach process due to overtopping failure during a flood. And that flood level would be water at the pond would be at maximum flood level, depending actually what the design storm is or a PMP event is for the dam. The overtopping can cause washout of the embankment to a certain height or the full washout of the full height. If the failure of the embankment happens due to overtopping during an extreme flood event, usually it is assumed that the natural catchment downstream of the dam is at peak flow condition prior to failure. And that's called in the literature as incremental impact assessment. This graph here is from a recent paper published in 2020 by Gilde and his co-authors in Mine, Water and Environmental Journal. It's interesting because they had analyzed 85 dam failure cases in the database that they had, and they look at the number of the failure, maximum height, minimum height, and maximum release volume, and the cause of failure of the dam. If you look at this graph, the earthquake and liquefaction, out of that 85 dam failure, 19 of them was caused by this mechanism of earthquake and liquefaction. And then the second highest is overtopping and a slope failure. Another graph from the same paper from the same author, they analyzed that 85 cases. Out of the 85 cases, 46 cases of dam failure was on the upstream raised embankment. And this graph actually shows the mechanism that caused that failure in that upstream raise embankment. 30% of all of the failure was due to liquefaction, and 28% was slope stability. Simulating the dam break. There are several steps that need to be followed to do a tailing dam break assessment and simulation. Step one would be defining credible failure mode. We need to ask if the sunny day failure with maximum operating point level would cause causing a credible failure mode, or a post-flood failure overtopping during the design flood or the PMP event is a credible scenario. If failure of the dam during flood event while downstream catchment is at peak flow condition, if that is a credible scenario. If sudden failure of the embankment due to earthquakes or static liquefaction is a credible scenario. What we should keep in mind is we should always avoid creating imaginary scenarios which are near impossible cases and hard to justify. In other words, adding up multiple rare and extreme events on top of each other. Step two would be basic information and studies, including defining the study area, modeling domain, area of interest, and model boundaries, reliable topography information to develop the 3D digital elevation model for the study, catchment and downstream hydrology and flood study, operation, the details of the operation, including normal operating point level, maximum operating point level, and volume and location of the pond in the TSF. Step two would be site investigation and collection of the data from site. That will include density profile with depth for the deposited tailing in the deposit. Are the deposited tailings saturated? If they are not saturated, then the next question that we should ask ourselves is there any possibility that in the future, the tailings for any rainfall event, any storm event, or any scenario that the tailing can get saturated? Whereas the phreatic surface in the tailings body is also another question that we should be studying and find the answer to that. CPT testing and shear vein data from site, and then liquefaction study and assessment, and answering the question of are the tailings or embankment foundation material or any layer under foundation of the dam would be liquefiable. Then we have to define from the data, CPT results, shear vein data, all data collected from the site, defining the shear strength ratio. If the material are liquefiable, it will be post-liquefied shear strength ratio, K value that we need to define. If we don't have anything from the site, usually one of the conservative approach will be using the recommendation by Olson and Stark in this paper reference at the bottom of the page. This data usually for any stage embankment and the future raises of embankment, a lot of this data already is available usually for the dam that need to be extracted out from the previous study. Step 4 will be laboratory testing, which includes basic testing, PSD, SGs, and liquid limits. Raw cell testing if you want to get an estimate of the density profile in the deep deposit. Shrinkage limit density test with strength gain with density. Cyclic triaxial, cyclic simple shear to do the liquefaction analysis and residual strength. And then last but not least, the rheology testing, which includes bob and cup rheology and shear vein data testing to estimate the flow property and flow behavior, either a Herschel-Barkley model or Behnam plastic model parameter. This is an example of density profile actually measured on site for one of the projects. That is a density profile with tube samplers up to the depth of 35 meters. As you see, you can define different zone in the deposited tailings, then average the density of 155 for up to the depth of 16 meters here, and then a higher density of 1.65 been defined for this project to the depth of 35 meters. Shear vein data, CPT data from the same site to a depth of 30 meters, which has defined the liquefied shear strength profile for the two locations or residual strength after the material is sheared. Then the rheology testing will come from the laboratory testing is bob and cup rheology by bob and cup, and also the shear vein data as well to extrapolate to the higher solid concentration, which is beyond the capacity of measuring with bob and cup. Then fitting that model is usually the tailing slurry, the best fit model is the Herschel-Barkley model, but it can be simplified to Behnam plastic model as well. Ultimately, we are after defining the yield stress and viscosity as a function versus solid concentration, so that the model can, when the solid concentration of the release tailing from the dam, when it mixes with water or solid drops, can change and vary during the analysis. Step 5 is failure slope and release volume estimate. The equation that which we use for this analysis is infinite slope theory, which is the equation of derived from the stability of a long shallow slope. The theory assumed that after liquefaction of tailing, the tailing strength would be greatly reduced, resulting in slumping of the tailings until the tailings reach a slope where force balance has been achieved. Equations, as you can see in the screen, and the reference paper to that is paper by Kit Seddon in 2007. You can go and study it further if you are interested. But essentially, the post-liquid or the slope of the failure surface is beta, and it is a function of undrained post-liquefied shear strength and the total unit weight of the ash or tailings, or depending on what you're studying, and with vertical strength.
Hey, no cutting. This is
this section is an embankment with the material tailing deposited behind the embankment.
Excuse me, Behnam. Someone in the audience, in the online audience, has their mic on. Could they turn it off, please?
So I was just brutally assaulted and burning the line outside.
Hubie, turn your microphone off. Mute yourself. Mute yourself, Hubie. I don't think I can do it. I can't do it. Sorry. Thank you.
Shall I continue, David? Yes. Okay. This is an example of embankment section. If the analysis shows that a weak foundation is underneath of the embankment, failure surface goes through the embankment, the foundation, you can define, based on the investigation from site, you can define as many layers you want in the tailing deposit to get more accurate, estimation of the release volume, or also the parameter for the tailing. Here we define two different material with density strength, density of 1.55 for the upper layer, and density of 1.65 for the lower material in the lower layer, material 2. And that post-liquefied shear strength ratio of 0.05 for the upper layer and 0.07 for the lower layer, which defines the equilibrium failure slope for the upper layer with 2.5% and the lower layer 3.5%. So the failure surface can be a multiple sort of slope and a shape that is best estimate the volume release from the embankment. That's applying that method to the embankment breach of 500 meters during the earthquake scenario, and with a slope of 2.5%, assuming that all of the tailings in this condition for this example is saturated and liquefied tailings. If the tailing is not saturated, this is a CTD, central thickened discharge, with the tailing not saturated. That's the concept of design for central thickened discharge. And you see, as you see, the tailing release volume is significantly reduced, and the slope of failure is 12.5% if the tailing is not liquefied and not saturated. For each, if you're analyzing the overtopping and piping failure, then we need to define the breach parameter. In the literature, you can find different method and models proposed for that. All of them are based on regression of the previous dam failure. More recently, in 2014, a paper by Knight and Froelich, they analyzed 88 dam failure cases from database, and they concluded that out of that, the parameter that's been reported for that 88 Dambreak cases, the Froelich 2008 method provided the best fit for the breach parameter. The Froelich method is a regression method that defines the average breach width and the time of breach based on volume of release and the height of the breach, which comes from the previous analysis, step 3. Then you need to, with the volume released from the dam, we need to analyze and route the hydrograph through the breach to get the hydrograph shape. If you have got a large water pond sitting on the top of the tailing, or the water pond next to the embankment that will be first released from the after the dam break scenario, then the first part of the hydrograph will be water only. As you see in this hydrograph, up to this point is water only, and then the second part of the hydrograph will be tailings and water. The step 7 will be simulation of the failure scenario, selecting modeling tools with non-Newtonian flow analysis capacity and also the capacity to consider solid particles. Assuming water-like property for tailings dam break analysis, we have to remember that it will not necessarily produce a conservative assumption and a conservative result. Always check the fundamental mathematical model built into the software package and make sure that as a minimum, it includes the turbulent terms in the energy loss equation. There are several modeling tools available in the market, from Flow 2D, River Flow 2D, Flow 3D, and DamW, and a few others, that they have that non-Newtonian flow capacity. By using those software models, we have to know that none of the commercially available model software packages are developed for the slurry or tailing flow. Most of them have been developed for simulation of natural river mud flow. And there are differences between the two simulations. No analytical or true semi-empirical solution exists for turbulent flow of a slurry in open channel, but some of the existing model can be modified to provide a reasonable approximation for dam break analysis. This is the fundamental model for the head loss in Flow 2D, which has got the 3 terms, yield stress term, viscosity term, and the turbulent terms for the head loss calculation. Although this is very rough and crude estimation of the head loss for non-Newtonian fluid flow, but reasonably acceptable for dam break analysis. Also, we have to keep in mind that using simulation tools or software that only have laminar regime equations as the built-in model will cause the over-prediction of velocity, of flow velocity, and under-prediction of the flow depth. One other thing to remember is, as long as the fundamental equation for turbulent flow of non-Newtonian fluid in open channels containing solids is not improved, using more sophisticated numerical modeling techniques such as CFD for dam break analysis or similar sort of problem would not increase the accuracy of the analysis and the accuracy of the result. I just want to share with you a few seconds of the two videos that I'll start both of them together. The top left one is few seconds of Berg-Medina tailings dam failure, and the bottom left one is the tailings discharge from a spigot at a TSF, active TSF. Let me just start the two videos, and I want you to just look at the two phenomena together. Over the last 15 years, we have heavily invested in research and development of model to understand what you could observe in this video, which is the tailing discharge, thickened tailing discharge on the beach and beach development. We have developed multiple models. We have sponsored 3 PhD research work, including my PhD research work, and we developed several published models on the open channel flow of non-Newtonian fluid thickened tailing slurry, which is very similar to the release of slurries in the dam break scenario from a dam. The same mechanism, the same equation, the same fundamental applies to both flow. One of the recent one that latest PhD research work, which we did with collaboration with RMIT University, is Dr. Javadi, 2017, which ended up in developing a model for fully turbulent flow of non-Newtonian flow in open channel and also transition regime. With this model, we currently use it for open channels flow, but we are working on that to develop, to apply it to tailings dam break simulation as well, and it is a work in progress. The accuracy of this model or other models that will be developed in the research paper by others, few of them in the available, is improves significantly accuracy of the dam break or similar problem to a dam break analysis. Step 5 would be what to expect from the simulation, reliability, and interpretation of the result. Doing a non-Newtonian fluid analysis for a dam break, you can expect that more realistic outcomes in comparison to water-like flow analysis. You can define the flow depth and velocity relationship. Flow, and also, one of the important things to remember that when you're analyzing a yield stress material, the flow at some point will stop. That example, the right-hand side in the screen, is a low yield stress assumption, the same volume released from the dam, but low yield stress assumption for the material, and then high yield stress assumption for the material released from the dam. As you see, for high yield stress material, the footprint that will cover would be a smaller footprint. At some point, it will stop from flowing. Well, while if you analyze it like water, it never stops. Actually, it flows until it reaches a point. Then you can do sensitivity analysis and to see the result and impact of that analysis, sensitivity analysis, to the outcome of the dam break with that non-Newtonian flow. One of the other things that you can get out of this analysis is inundation mapping, inundation depth, inundation velocity, with like any other dam break, analysis. Then the progression of the tailing flood or at the downstream at different time, and time to peak, like 2 minutes, 5 minutes, 30 minutes, and 60 minutes. Other thing that you can do, you can analyze and design the protective dike to protect actually the downstream infrastructure from inundation. This is another case that is studied that the dam, this tailings release from this dam is with the assumption that the tailing would be saturated and liquefiable. This is inundation depth, inundation velocity, and time to peak, and the progression of the flood wave from the dam and the housing of downstream of the dam and the arrival time. Again, the same failure, the same actual location, the same dam, the same volume, but comparison to a situation that the dam and the tailings in the dam keep unsaturated. If the tailings are unsaturated and you can ensure that during the operation of the TSF will never get saturated, or the pond will always be far away from that location that you're doing analysis, then the dam break failure would be reduced to a geomechanical failure with significantly reduced volume release and footprint that would be significantly smaller than downstream. Here again, the two videos of the similar sort of dam break with the same volume of 1.5 million meter cube from the dam with low yield stress and high yield stress material assumption, just to show the difference between the two analyses. I start the two videos together. The top left one is with the low yield stress of 5 Pascal, and the bottom right one is 5,000 Pascal. As you see in the 5 second or 14 second, the low yield stress material will come to the boundary of the model, and the material will escape from the model, go out of the model. As expected, the high yield stress material will move slower and create a deeper inundation at the downstream area. At the end of the model, when it comes to 120 second or 120 step, I have to say, if you see, pretty much all of the material from this low yield stress material has gone out of the model, but this material here, the darker color in the right bottom right, is still in the model. And if you run the model for longer time, still you see that the material that deposited here will stay there because of the yield stress effect. So a deeper actually inundation will happen with higher yield stress material. The result of dam break then can be plotted in the flood vulnerability curve here to get in terms of maximum velocity, d multiplied by V hazard classification, flood arrival time, and flood propagation. Then consequence category of the dam based on the population at risk and possible life of life can be determined from the study. Uncertainties in the input parameter and sensitivity analysis. For every dam break, regardless of how much effort you put to site investigation or laboratory testing, because of the variability of the site condition is always will be uncertainty input parameter, and that input parameter can affect the result of your analysis. So that uncertainty can be in tailing in situ dry density, post-liquefied shear strength, rheological property of tailing, yield stress and viscosity, and breach mechanism or geometry of outflow hydrograph. It's recommended that always undertake a sensitivity analysis to see the impact of variation in this input parameter on the tailing dam break analysis and the result. Without this sensitivity analysis, a dam break study would not be completed and it would be questionable. So the parameter may not have significant effect depending on the project, depending on the geometry, or may have significant impact. Thank you all, and that was the end of the presentation.
Now, Behnam, if I could get you to stop sharing.
Okay, I'll try. Did that work?
And we'll come back to you for Q&A in about half an hour's time. Get my fingers to work. I wish I had my mouse. Kathy, see if your fingers are any better. Let me move that down to share screen. So the mouse is moving randomly. Hold on a sec, I need to adjust the volume. That's 100%. Okay. Teething problems? So the last formal presentation is from Dr. Marcelo Llano, who's with Red Earth Engineering. He's going to talk about breaching, no pun intended, the gap between geotechnical and hydraulic engineering to improve tailings dam breach studies through large deformation modelling.
Okay, yeah, good night, everyone. Thanks for the invite, David. Thanks for organizing, Kathy. Before I start, I would like to ask you to raise your hand if you are geotechnical engineer, please. Okay, and how many hydraulic engineers? Okay, so most of the people are geotechnical, and we have some agnostic engineers. Okay, so a lot of my presentation is going to be, I'm going to speak a little bit about the motivation of why breaching the gap is important. I'm going to talk a little bit about flowability of tailings, what the mobility of those materials are. Then I'm going to talk about the material point method, which is why I specialize on, and large deformation modeling using the material point method. Then I'm going to speak a little bit about the effective stress concept, and that's the reason I asked you if you are a geotechnical engineer or a hydraulic engineer. So I know the audience, so I know that I probably need to stop a little bit there and talk about the effective stress concept. Then we're going to go through a number of case studies of dam breach analysis where material point method has been engaged. And then I'm going to finish with some summary and final thoughts. Okay, so these are a couple of notes from CDA 2021 technical bulletin from, this was published a number of weeks ago, so quite recent. So I took a couple of the statements that they made there. So I'm just going to read them because one, I want this message to get across. I was quite pleased to see what they wrote. So what they said about tailings characterization is flow liquefaction results in large deformations and directly impacts the volume of tailings that can be released during breach. When they speak about rheological behavior, CDA says the measurement of yield stress and viscosity are often conducted for tailings with a volumetric solid concentration less than 45 to 55%. So I'm going to stop here and I want you to think on what's the solid concentration of the tailings dam that you might be working at the moment. And you might realize that it's probably higher than that. Okay, and then CDA continues and says the yield strength and viscosity increase exponentially and become very sensitive to the solids concentration when the solids concentration is close to a threshold, illustrating the influence of water content and the rheological behavior. So when they speak about this threshold, what comes to my mind is like, okay, the liquid limit of soils, like which we in geotechnical engineering understand as a solid, soil behavior as a liquid, is around 1.7 kPa, okay? And it can range up to like around 2.3 kPa. When you have a soil in the plastic limit range, you are talking about like 100-fold that, right? So when they talk about like a threshold when the yield strength increases significantly, they're probably referring to like what the difference between the liquid limit and the plastic limit is. And it's just like 100-fold concentration. That's what increased they're mentioning there, which are like clearly concepts that are related to geotechnical engineering. But we are talking about the hydraulical engineering here as well. So continuing with CDA, they also say, although the concepts of viscosity and yield stress are commonly used in conventional fluid mechanics to characterize the shear profile of a fluid, they can be inadequate to describe some non-Newtonian flows with high solid concentrations in which the particle-to-particle contacts become dominant and control the flow. So I want you to stop again and think, okay, what's the solid concentration of the last tailings dam where you work at, or like the tailings dams where you're working at? CDA also says at higher solids concentration, the mechanisms of compression and dilations may affect the tailings flow and should be taken into account. It also says integration of the principles of advanced soil mechanics in combination with fluid mechanics in rheology can be used. So some of you might know this plot. So in the horizontal axis, we have sediment concentration by volume. In the vertical axis, we have sediment concentration by weight. That's the notation that hydraulic engineering and some other disciplines may use. That's the notation that most of engineers might know, but geotechnical engineers like to talk in terms of water content. So I have intentionally added the percentages in the plot, which represents the equivalence of water content for each one of those volumetric concentrations, either by weight or by volume. You just need to be careful when you look at this plot, because that plot does not take into consideration the shrinkage limit. So like when you have a soil that it's losing water, you have a reduction in volume, but that only happens up until the shrinkage limit. After that point, volume of soil will stop reducing its volume. So what I'm suggesting here is like, you need to be tread carefully when you are in the upper portion of that plot, because the behavior of soil might change depending on your shrinkage limit. Okay, so tailings, or like granular arrangements and its properties can be predicted as long as you know mineralogy. And then the behavior of that material is going to depend highly on the water content. Okay, so in the plot that I'm showing there, and this is going to get a little bit complex, so I want you to slow down and read what we have there. So we have 4 different modes that indicate flowability of tailings, or flowability of materials for that matter, like it doesn't need to be tailings. So if you move to the right-hand side of the plot, then you have decreasing water content, right? So you can move from a water flood, which we already saw, like it's in the excess of hundreds of water content, and you can reduce to a landslide with decreasing water content to figures of around 30%, 20%, which is what we see in the field. And obviously, like, I mean, the flowability increases the other way around. When you have a water flood, of course, we're going to have a higher flowability. When we have less moisture content in our soil, we're going to have something that resembles a landslide. Okay, so the field where I perform, like I'm a geotechnical engineer, so like I'm around where that purple plot is. So I sort of know what I want to believe, that I sort of understand what a landslide is and how it behaves. And my colleagues from hydraulic modeling, when they deal with rheology, they are in the that other side of the slide. So they know very well how to do water flood, like mud floods and mud flows. Okay, and as you can see, there is a gap there, because so we approach from one side when we want to tell to our clients slope stability. That's what we sell. We tell the client, okay, this is your slope, it's going to be stable, right? So, and what I'm going to show you next, and it's quite unfortunate that we have that label there, but we're going to see a bunch of wide squares that is going to place in that plot. And the relative position of those wide squares are going to indicate where that technique is applicable to the phenomenon that you see in the middle: water flood, mud flow, or a landslide. So obviously, I'm going to start with what we know best as a geotechnical engineer. So when we speak of limit equilibrium, we are talking about slope stability. So we are also talking about, like, there's no deformation there. Things just stay static. As soon as you move towards like a landslide behavior, landslide-like behavior, we are talking about like a stress strain. And usually what we use in our practice is a small deformation approach. That's what you see in FLAC or like Flaxis, or whichever provider you like, right? Then when you are in the mud flows, you will be seeing like flow slides, debris flows, slurry flows, avalanches. And obviously when you look and when you move to the left-hand side of the plot, like you're gonna see your inundation modeling. I just highlighted there like some of the providers there that can provide you with a solution to model those processes, but there are many others on the market. And this is where it fits, or like where I'm trying to sell you fits. Large deformation modeling, Mpm. So go back one, like you might notice there is a gap there. Your flow slide, debris flow scratches the surface of what a geotechnical model is trying to achieve. And your stress strain and deformation in soil mechanics does not even touches what this processes can get to. And that's what I meant, obviously with the pun intended, like we are trying to bridge the gap between what geotechnical model is and what hydraulic modeling is. Obviously, there is an overarching phenomenon here that we are not going to talk about, and no one has talked about much because it's quite complex, which is erosion modeling. And erosion modeling can trigger like pretty much any of those events over there. Okay, so what's my background with Mpm? So actually, I was talking with Luke earlier today, and I was like, it's roughly a decade. It was October in 2011 when I started writing my first paper on Mpm. The name of a master thesis is Material Point Method Applications to Geotechnical Engineering Problems. In 2016, I finished my PhD in geotechnical engineering at the University of Brasilia with an externship at the GEC in the University of Queensland, where I met Dave. And the title of my thesis is Experimental and Numerical Study of Geotechnical Engineering Problems Using the Material Point Method. We have published an excess of like 30 scientific publications, not all of them related to Mpm, including 2 papers in geotechnique, and some of those papers has received an excess of 100 citations. Okay, so I'm going to be jumping back and forth to, I'm going to be talking to the geotechnical engineers in the room and to the hydraulic engineers in the room. So this slide in particular is directed to geotechnical engineers. So finite differences, which is what FLAG runs on, was introduced by Taylor in the 1700s. Finite elements, which is what Plaxis use, was developed in the 1940s. Both of them are used to tackle complex engineering problems for which there is no analytical solution based in a continuum mechanics approach. So there is a problem there because the traditional formulations that we have already established that exist are not well suited to tackle large deformation problems. And this is again talking from a geotechnical engineering perspective. So the alternative approach is to use mesh-free or meshless methods, which Mpm fits within. And these methods can solve the problem of simulating large deformations. So to the left-hand side, you see a slope instability being modeled using the finite element method. And you see a region there where the mesh gets a large deformation, the mesh gets entangled. And actually, these techniques are not well suited when something like that happens. So you can actually, you need a technique that can handle this. You need to look further. The problem, or like the circumstance, is like large deformations are quite common in geotechnical engineering. SPT, CPT, DMT, fault contest, landslides, dam failure, piling. All those are phenomena that deals with large deformations. I have some pictures here to exemplify them. And as I said before, like classical numerical techniques fail to deal with large deformations. Again, this is coming from a geotechnical engineering perspective. So, okay, so what's Mpm? So Mpm, what says is, okay, you have a background mesh, which is your universe, like that's where like your slope is allowed to exist. And that mesh is gonna compute everything that happens within the universe. And then within that universe, you have points. And those material points have finite dimensions and represent the actual discretization of your slope or your pile or your CPT probe. And they carry all the relevant information as they move, and they're free to move across the mesh. So what's the development of Mpm through the years? So this is nothing new. Like, I mean, this started in the 1960s with a particle in cell method formulation, which was actually developed for fluid mechanics, not for like solid mechanics. It was only in the 1990s where it was extended to solids. And the first application in geotechnical engineering was almost in the 2000s. The first application into the tailings dam industry was for the Aznalcóllar case, or Los Frailes in Spain. Their 2017 ranking lecture has an emphasis on Mpm application for landslide motion. And I'm including some of my work here because between 2017 and 2017, we developed a number of conceptual models for various runner examples when I was working at the GEC and at UQ. In 2019, I had the opportunity to apply the MPM modeling to the Brumadinho failure, and those results were included in the expert panel report. Since then, in 2021, MPM modeling has been done for Kenya. That was done at Virginia Tech upon my recommendation to ALBA. And then in 2021, there's been a number of contributions to the development of Tailings Dam Breach Analysis. Luke shows some of the results, and we have applied some of these techniques as well at Red Earth Engineering. Okay, so this is how MPM looks like. So of course we have seen this, like maybe on the move, maybe on the news, so or hopefully not in your workplace. Failing wall retaining wall. You can fail a retaining wall either by like active pressures, which is what you see in the left hand side. That's animation, and then but you can also fail it through passive stresses, which is what you see on the right hand side at the bottom. You can also apply MPM to slope stability and also to erodible barriers, which is what you see at the bottom. And there is software available to develop all this kind of modeling. There is nothing commercial, and there are several research packages that exist. This is some of the ones that are out there. The one at the top is the one I recommend, which has been developed like those universities that you see in the bottom. The name of the software is Anima 3D. I do have like good relationship with some of the developers of the software. So I want to do like a pause here and just like summarize briefly like what we discussed so far. We have discussed so far. So we know that large deformation is a common occurrence in geotechnical engineering. We have learned the behavior of large deformation. We have learned how to deal with it, like in fields like pile driving, for example, or when you want to apply the site densification for a structure. But we face some challenges, and one of them is because like geotechnical engineers, we have been trained to learn to perform calculations to avoid failure, which in our field is understood as large deformation, either large or small, sorry, deformations, either large or small, of a given slope or a dam. So despite significant progress in computational capacity, limit equilibrium with no deformations are our bread and butter every day. However, limit equilibrium is going to be challenged more often, but it's unlikely to disappear. Earthen structures are only going to grow due to commercial demand. International standards and guidelines are going to become more refined, and the obvious next step is to widely adopt small deformation approaches, which are readily available for everyone in the market. Okay, so this is why I asked you the initial question when I started my presentation, is because I want to understand, okay, do we know what effective stresses are? We don't know it. So a couple of Google searches on the internet, and I really like the first definition. Effective stress can be defined as the stress that keeps particles together. In soil, it is the combined effect of pore water pressure and total stress that keeps it together. So effective stress is what bonds soil particles, right? And pore water pressure is what tries to break them apart. The most common notation for effective stresses is using the vertical effective stress, which is what I have in the first equation over there. And we like it because it's very easy. But there are more sophisticated versions of it. We have the Cambridge notation, which is the second row of the equations. And we have the MIT notations. Some authors use P to refer to S, which make it a little bit confusing, depending which book you're reading. But I mean, that's how life is. Life's not easy. The reason I mentioned like the three notations there, it's because the plot that you have on the left-hand side, So you see like all those vertical stresses over there. I'm sorry, I'm just gonna move from the camera. Look at these arrows that you see on the side over there. So you can see some horizontal arrows, like there is more than vertical stresses. There's horizontal stresses, and unfortunately we don't know enough about horizontal stresses, but they do exist, they need to be taken account for. Okay, so again, so talking about effective stress concept, strength, and rheology. So usually when you go to a specialized lab and you ask like for rheological characterization, you're gonna get something like this. You're gonna get a yield stress curve that shows you the progression of strength with solid mass fraction, and you're also gonna get a variation of shear rate with shear stress for like different solids content, right? But we were told that soils are also affected by the effective stress concept, so we don't really get that information. So does it really apply? So reading through the literature, I found this paper. It's called End-like rheograms of suspension of magnetic nanofibers. And it's the characterization, the rheological characterization of a slurry that has magnetic particles on it. The behavior of those magnetic particles upon shearing defines what they call the end-like rheogram, where you have a peak at low strains, then you soften, and then you harden again. The authors go further and say, okay, you can deconstruct that behavior and draw the green plot. So draw the green line that you see there. The green line is number 1 for those of us here. We can't really see it very well. And then you have the red line, which is number 2. Okay, so you have like that behavior, which looks a little bit funny, but you can decompose that behavior between 1 and 2. And you say like, oh, well, okay, like that's rheology. Like you have that behavior on magnetic particles. Why are you showing that us? Why are you showing that to us? So in the plot to your left-hand side, you're gonna see the magnetic field that was applied to those particles. So if you look closely for like a lower magnetic field, you're gonna see lower underend shear strength. As you increase your magnetic field, your underend shear strength response increases. Okay, so, and when you think about magnetic fields and the shear strength and the effective strength concept, they are not that dissimilar. And the reason like this paper caught my attention was because please have a look at the broken line they plot in the middle. How does it look like? That plot looks very similar to the tailing characterizations that we performed for one of our projects in Red Earth, which is the plot in the top left. And you can pretty much see that end-like behavior of those stress strength curves. We achieve that end-like behavior by increasing the confinement stress of our tailings. So there's definitely some evidence that there is a different response of your mechanical behavior with different confinement stress. Going back to thinking again on our previous slide, when we broke down like that behavior that we see in the top left of the figure, like they broke that up into different behaviors, like one that only increases and one that increases and then softens. Then we can also think on the characterization of recent tailings dam failures. So on the left-hand side, you have Caria. That's the tailings for Caria. And on the right-hand side, you have Brumadinho. I'm going to go one back. If you look at number 1, it looks very similar to Brumadinho. And if you want to use your imagination, you can think a combination of these two curves, 1 and 2, that can give you the behavior of Caria, which is highlighted by red in the plot in the left corner at the bottom. Okay, so it seems like the effective stress concept has an effect on the rheological behavior of tailings. So how do we model it? Well, so brittleness, which is what how we describe this kind of behavior, may be simulated by introducing a strain-dependent parameters that control the transition between peak frictional angle or peak cohesion to residual frictional angle or residual cohesion. And the softening behavior is accounted for by reducing the strain parameters that with the accumulated plastic deviatoric strain. Okay, so I want to make another pause here to summarize what we had just discussed. So the effective stress concept has been known to have influence to the mechanical response of granular arrangements during loading. Specifically, a Mpm model can simulate the initiation of a failure in the transition between static, being solid, state through a deformation process that can result in liquefied tailings. Limited rheological testing under confining stresses exist. Available results suggest that the confining pressures have an influence in the rheological response of materials, especially during the solid to fluid transition. A detailed study about the role of different constitutive models in Mpm simulations of granular column collapses is presented by the Fernand Soga, 2016. Now I'm going to move into a number of case studies, some of which I have authored, and some of them are being done for some others. So this geometry is actually the geometry that you see in Kenya. The tailings in Kenya weren't actually liquefiable. The tailings in Kenya, sorry, no, this is not Kenya, this is Mount Poly, my apologies. So the tailings in Mount Poly weren't actually liquefiable, and the reason they flew was because they were eroded with the ponded water on top of them. Nevertheless, we use this geometry to try to understand how, from again a geotechnical engineering perspective, the dimensions of your tailings storage, which is represented by the storage length in the plot at your right-hand side, will affect your runout, but also taking into consideration what will be the undrained shear strength of your tailings. What we conclude in this study is like, I mean, the tailings storage length didn't actually have like much of an influence. And the main driver of the runout distance was the undrained shear strength. This is a study made by other author. This is Nalcoyar or Los Frailes, done by Zavala in 2010. So Los Frailes failed due to an increase of pore water pressures along like a weak plane, where some brittle behavior was observed. The brittle behavior is represented in the plot at the bottom right. And what I want to highlight here is the resemblance between the geological survey, which is the plot, which is the figure in the top left, and the Mpm model, which is at the bottom left. Obviously, you can argue there are some differences there, but there are also like some resemblances. This is the Brumadinho model. This was a model we have the opportunity to develop for during the expert panel review process. I am citing here exactly what is written in the report. I don't want to say anything that is not written there. But basically, the text in the left describe step by step what it was seen during the failure in the video recording and in the Mpm model. So at 2 seconds of failure, the total velocity indicated that initial signs of failure were observable in the upper section of the dam. At 5 seconds, the deviatoric strain reaches unity at the toe of the dam and propagates upwards behind bends. The limit of the deviatoric strain regions of around 1 indicated by the orange arrow suggests the position of transverse cracks seen on video recording from Cam 2. At 7 seconds, the concentration of the deviatoric strain equal to unity at the toe, and the purple arrow shows bulging. The green arrow shows the concentrations of deviatoric strains equal to 1 in the location of the back scarp that you can see in the video footage. The plot in the bottom left is the estimated velocity outflow of the Mpm model. The last case study I have to share with you is the Iscaria, which was done as part of a master study in Virginia Tech, was published this year. We are all more familiar with this case because we're in Australia. So I'm not going to go into the details of the case, but I just want you to see the progression of the deviatoric strains. We show you where the failed zones are. And I want to draw your attention to the second figure here in this slide, which shows you the locations of the pump house initially, which is the rhomboid figure drawn in black. And how does it look like at the end, either in the Mpm model or during the field observations. So the resemblance was quite remarkable. The key drive, like the study found, like the key drivers of the observed behavior were residual properties of the foundations, the rate at which tailings liquefied, the initial extent of liquefied tailings, and the presence of the excavation at the top of the dam, as we already know. The softening characteristic of the foundation played a large role, allowing for the failure to occur. Without the progressive softening of the foundation, the dam does not move without the liquefaction of tailings. Summary and final thoughts. So we have covered related aspects of the numerical modeling of tailings dam breaches from a soils mechanics perspective. The review covered mobility of tailings, the role of large deformation modeling in TDDA, the relevance of the effective stress concept in tailings dam breaches, and several case studies. Mpm is a growing technique. There is still no commercial software available yet, but there is a vast technical source on the web. Despite all the advantages mentioned, there's still limitations. Applicability is still limited to 2D problems. And we have saved these limitations by coupling the Mpm outputs with hydraulic engineering software, as Luke presented earlier today, which results in a better product for the clients, actually. The publication of the recent GISTM with emphasis on alarm concepts and the new CDA bulletin will likely accelerate the wider implementation of this kind of technique and other similar type of approaches in the industry. I want to thank the Queensland Tailings Group for the invitation, and Red Hand Engineering, all our leaders in the company. Thank you very much for the opportunity to apply all this readily to all our projects. Also, thank you very much to David, because everything that Luke presented related to Mpm and everything that I presented related to Mpm is actually thanks to David. Like when we met in 2014, wow, 2014, David had the vision that this might have applicability for the industry. So this is a reminder to everyone of the role of research in our industry. I've had many industry partners saying, or like with the frustration of like, oh, but all this money goes into research and we never see an outcome out of it. Well, you do, and like you might not see the outcome today. Mpm was developed back in the 1960s. So if someone had said back in the day, like, oh, let's not do this because there's no direct applicability, like today we wouldn't have the benefit of applying all this. So it is a reminder to everyone to support development, support the consultants that are there that are willing to apply like new concepts to reach new boundaries, to support research, to support universities, because they play an important role in our practice. And what we develop today is, at the research level, is what is going to be used in 50 years from now. Thank you very much. That's my email if you have any questions or if you have any queries.